Hi friends, in this session we are going to determine the natural frequency for a torsional system in single degree of freedom systems. So consider one torsional system where there is one shaft which is attached to the disc. So this is the disc and this is the shaft. And when we apply the torque on the disc, then the vibration which are generated in this system, that we'll have to see. See, normally in torsional system, this disc will act as mass and this shaft will act as a spring. Means it is nothing but a spring mass system, as we have earlier seen for the single degree of freedom systems. Means we can relate this system with a simple spring mass system. For the derivation of this torsional system, we will require the help from the derivation of a single spring mass system by using the Newton's method. If you have not watched that video, then please do watch from the playlist, that derivation for single degree of freedom system by using the Newton's method. Please watch that video and then come to this torsional system. Now I'll represent this system into the isometric form so that it will be very much easy to view. So suppose this is the disc and this is your shaft. Now consider this is as mean position of this system. If I apply the torque on this system, then this system will rotate and the angle turn will be equal to theta. Means this theta is nothing but the displacement of this system, and the torque is nothing but, in linear system we consider the whatever the things are required from the linear system. I'll write here. In linear system we consider force. In angular system we'll have to consider the torque. In linear system the force is equal to ma, and here in angular system we convert into the torsional system. So instead of mass there will be mass moment of inertia, and instead of acceleration there will be angular acceleration. So this torque is nothing but I alpha, okay, and this you can write as I theta double dot. Okay, so the convergence in linear system force, in torsional system theta. In linear system displacement is x, in torsional system displacement is theta. Okay, in a linear system we require the stiffness k. In normal torsional system it is normally represented by kt. In linear system acceleration is a, in torsional system acceleration is alpha. In linear system the mass is m, in torsional system it is represented by I, that is the mass moment of inertia. So these are the convergence that we require for this torsional system. Okay, so with the help of this convergence it will be very much easy to understand this system. So here I have applied the torque, and because of this torque there is angular displacement, and this displacement is nothing but theta. Now this shaft will act as a spring, so its stiffness is k or kt. Normally in books it is represented by kt, that is the stiffness of this shaft. This disc will be having the mass moment of inertia, and its mass moment of inertia is I. In some books this mass moment of inertia is represented by j, but actually in normal condition we represent mass moment of inertia by I. So the disc is having mass moment of inertia I, its angular displacement is theta, and the stiffness of shaft is kt, which is subjected to torque I theta double dot. Now to solve this system we will have to take the help from the derivation for single spring mass system. So just quickly we'll go there and we'll take the review of that particular system. So see, I have uploaded the video of the single degree of freedom system by using the Newton's method. In this Newton's method, here you can see the displacement of this mass is because of the self weight, this displacement is because of the externally applied force, and here the most important thing which is required for our torsional derivation is we require the restoring force and accelerating force. Here this system is linear, so here we have restoring force. In our system, in torsional system, instead of restoring force, we will have to use restoring torque, and instead of accelerating force in torsional system, we will have to use accelerating torque. So we are going to take the help from this one. Okay, so the restoring force you can see here minus kx, and from that directly I am going to write for our torsional system restoring torque. In linear system it was restoring force, and that restoring torque was minus k into x, but we'll replace here with these notations. So minus k means kt into x, that is theta. So minus k theta. Okay, so we have replaced that minus kx by minus k into theta. So this is the accelerating torque. I'll mention this as equation 1. Then next one is accelerating torque. In linear system it was accelerating force, and that accelerating force is nothing but F is equal to ma. So here the accelerating torque is T, and T is nothing but I alpha, and we can write this I alpha as I into alpha means theta double dot. So this is the equation number 2. Okay, so from or by taking the help from the Newton's method, we have directly written here restoring torque and accelerating torque. If you want to write these two equations from this disk, then it is very much difficult. So keep remember, you have to take the help from the Newton's method and directly write these two equations. So when we write these two equations, then for equilibrium condition, this accelerating torque will be equal to restoring torque. So I'll write for equilibrium condition, accelerating torque will be equal to restoring torque. Now write the accelerating torque from equation number 2, that is I theta double dot is equal to restoring torque, it is minus k into theta. Okay, now transfer this minus sign on that minus term on that side. So I theta double dot plus kt into theta is equal to 0. Now to convert into standard differential equation form, divide by I. So theta double dot equal to plus, here we have plus kt divided by I into theta is equal to 0. So this is nothing but the differential equation of torsional vibration, but we know that the vibration is with SHM, so we'll have to compare this equation with differential equation of SHM. So here I'll write differential equation of SHM. What is this equation? It is x double dot plus omega square x is equal to 0. But here we have a torsional system, means angular system, so convert this into the torsional system. So instead of x, write theta, so omega square theta equal to 0. Now compare. So here we have theta double dot, theta double dot. Here we have theta, here we have theta. Here we have 0, here we have 0. So ultimately, after comparison, so comparing with differential equation of SHM. So after comparison, we can directly write omega square is equal to K by I. So omega square is equal to K by I. So take the root. So omega n is equal to root K by I. So this is nothing but the circular frequency. And if you want to convert into natural frequency, then natural frequency Fn is equal to 1 divided by 2 pi omega n, and omega n is nothing but K by I. Okay, so this is the natural frequency of the system. Okay, so this is the natural frequency of the system. So I'll revise quickly. So I have converted a single spring mass system into torsional system, where I have given one disc with the mass moment of inertia I. There is one shaft which will act as spring, so its stiffness is K. Because of the applied torque, the angular displacement is theta, and this applied torque is nothing but I theta double dot. So the restoring torque I have taken directly from the equation of Newton's equation for single degree of freedom for simple spring mass system, and it was there minus K into x. So I have converted into angular. Then accelerating torque is equal to I alpha, so I theta double dot. For equilibrium condition, the accelerating torque must be equal to restoring torque. So this is the accelerating torque, this is the restoring torque. So transfer this term, convert into standard differential form, compare with SHM, differential equation of SHM, will get the natural frequency of the system. Okay, thank you.